Hi everyone, welcome to the next lecture on machine learning from egate.ai. I am Dr. Amrith Krishna and today we will be learning about decision trees as our next in the classifier series. So let's have a look into what exactly are decision trees. So if you see the key issues in machine learning, it includes probably three broad categories or three broad aspects. So one is the modeling aspect, where we see how to formulate your problem as a machine learning problem. There it further asks for how do we represent the data, which algorithms to use, and what learning protocols we must use. So within that, we further need to see what are the good hypothesis spaces and good features. So again, what is a good learning algorithm? How exactly we measure the success? How do we identify generalization as against overfitting? And finally, how exactly will the learning take? So far we have looked into logistic regression. We have also looked into naive Bayes. So one of them is the logistic regression is a discriminative algorithm. Now naive Bayes is a generative algorithm. Now we will look into decision tree. It is another discriminative learning approach. And we will see how it is different from others. So to start with, the natural question that arises here is, what are decision trees? So we can say that decision trees as a hierarchical data structure, but here we are talking about classifier, which is basically about learning a function, and now all of a sudden we talk about data structure, right? So the data structure that we are learning, it has to be, or in, I think I spilled the beans, we have to learn the decision trees. And we have to do that using an algorithmic approach, which we call as the ID3 algorithm. And we will see how we use both of these. So how we see that, how we arrive at decision trees, or amongst the possible different decision trees in a possible hypothesis space, we will see which one to choose and how can we use a learned decision tree to make a prediction for an unseen instance. We will also see what is the expressive power of a decision tree, or what all can be expressed in decision trees or using decision trees. So let's have a look at this. Representing data. So we can definitely represent our data as a big table. So if we see the table here that we have shown here, you can see that there are 6 rows, right? There is 1, 2, 3, 4, 5, 6. So there are 6 rows. Let's say the second row is this one, where we have the name of a person, Peter Bartlett. And there is a label which happens to be the plus sign or the positive label, right? So we will say that each row represents a data point. Now, it is fairly easy for us to imagine a large database with thousands or even millions of data points, each represented in a row. So it can be few thousands or few millions. We can still think of a table that can handle all of this. So one of the issues with the representation that we see here is that if we just put our data with just the names and no other representation of the defining features of the data, then it cannot handle unseen scenarios. So, in other words, just putting the names will not lead to generalization, something that we are very interested in learning. So, it's no generalization, just putting the names. Well, there is nothing much to be worried about here. We all are aware of this issue. So let's see how do we fix this issue. So instead, we can think of each input as a representation consisting of a combination of features that are relevant to the task. So if you see here, instead of just writing the name, which is Peter at this point, which is the second row, what if we represent the same thing but as a set of features? As you can see here, the column names. So I have decided to choose 4 features as of now, and we represent each name in these 4 features. So at this point, I have not mentioned the task. For the time being, let's assume the following features will be helpful for our end task, because typically the features have to be decided based on the task at hand. So currently we have 4 features, and these features are: does the name have a punctuation? What is the second character of the first name? Is the length of the first name greater than 5? Are there same first letter in 2 names, etc. So depending on that and depending on the name, we have extracted the corresponding values. For example, Claire, so no one has a punctuation in the name. Claire's first name has L as the second letter. Peter's second name has E as the second letter. The length is greater than or 5. Whether the first name and last name have the same letters, there is a yes or no, and of course the label as given, right? So please note that this name column is not part of the features because it does not generalize. Instead, maybe let me cross it down. Instead, my input, which corresponds to Claire Cardi, reads as no, L, yes, yes, minus. Or my input representation that I will show the model, or I will show the ML algorithm for Peter would be no, E, no, no. So now this is how the feature representation for the input is done. Now I have a quick question. With these columns, how many unique rows are possible? So if you see here, we so far have seen 6 data points. So there are 6 rows and we have the corresponding feature representation for them. But how many unique such rows can be represented with the current feature set? This is precisely the question. So if you see here, this is the feature 1, the name has a punctuation or not, is a binary feature. Like it either has yes or no. It's binary. Length of the first name is whether it is greater than 5. So the answer is either yes or no, which means again 2, right? Again 2. I'm sorry. The feature same first 2 letters, it's again a yes or no question. So again 2. The second character of the first name, there are 26 different possibilities. I am assuming case folding. The second letter generally cannot be capital. So I am assuming case folding nevertheless. So it's A to Z giving 26. So how many unique such letters? So it's 2 cross 26 cross 2 cross 2. So it's 8 cross 26. I think that's 2, not 8. Yeah, 25, 8, so 200. Yeah. So there are 208 different unique possibilities that we can achieve with the current feature space. So now think of a scenario where instead of 4 features, so we said we have 4 features, right? So instead, let's think of 100 features. We can extract 100 features from data. Even from this name data, we can extract 100 different features, but let's say we have 100 features. And let's avoid some complexity. Let's say that every feature is a binary feature. So even if you assume the simplest possibility, right? Because if there is a feature, it has to have at least 2 possible values. If it has just 1 value, it is not providing us any valuable information, so that feature should be ignored. So the minimum a feature should have is 2 values. So if I'm assuming the minimum value that a feature can take, the minimum number of values that a feature can take, then also we will have 2 power 100 possible rows or unique rows with 100 features, with 100 binary features. So think about it. We have 2 power 100 unique rows that needs to be stored if we have 100 features and if we have so many data. So try to understand that this is realistic more often than you can imagine. So just storing them in a table need not be the most efficient way, or need not be a pretty advisable way even to do this when we deal with large data sets. And essentially we need a more compact way to represent the data. We need a more compact way to represent the data. And probably you already know where I'm heading with this. Decision trees are here for the rescue. So decision tree is a hierarchical data structure that represents data using a divide and conquer strategy. Now it also happens that this data structure can also be used as a hypothesis space. So we discussed what is a hypothesis space. It's a space of possible hypotheses or functions, and the hierarchical data structure that we use to compactly represent our data can also be used as a hypothesis space. A decision tree learner explores this hypothesis space to construct a decision tree that fits the data set. So given a collection of examples, there is a better way to say it, given a data set, a learner, what does it do? Explores hypothesis space to construct a tree or a decision tree that fits the data set. Yeah. So decision trees are a family of classifiers for instances that are featureized. I will simply say featureized. Now we said that they are trees as in the graph structure tree, and naturally, if it's hierarchical and if it's a graph structure tree, then naturally for every graph there are nodes and edges. So for decision trees, every node is a test for an attribute or a feature. So nodes are tests for feature values. Now, what can be these tests? It can be, it basically, a test is basically something saying that given a feature or given a condition on a feature, whether the answer is a yes or no. So is the value for the feature is an yes or is it a no? For instance, if you look at this is precisely a good test, right? Probably the feature is length of the first name, but I can do the test as length of the first name is greater than 5 or not. Now, there is one branch for every value the feature can take. Now, for example, if the feature is asking here, what is the second character of the first name? Now, that means that feature has 26 possible values, and for that feature and every value, I can do a separate branching. So just to make it understand here, so let's say second letter is the feature, and I can do an edge or a branching for everything from A, B, C to Y and Z. Now maybe we will build more nodes depending on other features. We will come to that later. Nevertheless, once I have terminating nodes, this is like the leaf node, right? So the leaves of the tree specify the class level. They finally tell you the class level. Say it is positive. Maybe this one will tell you that yes, it's positive, something like that. Maybe there is something else somewhere here that tells you negative. Yeah, maybe to avoid confusion, let me clarify it. Yeah, there is something internal. Yes, there is a plus, there is a minus, depending on the value. Let's say this is F3 or F2, val1, val2. Depending on the value, there is a decision. So there is a tree. A tree is built. The nodes are the test for features, unless it's a leaf node. For every value of the feature, there is a branching out, which is an edge. And the terminal nodes are basically the labels. Now let's see what are we saying here. So let's give an illustration of how decision trees can be useful or how decision trees can be put to use. So let's consider a data set of shapes. So let's consider a partition of the data set into 3 groups based on the labels assigned to them. So we have a lot of shapes. We have some circles or ellipses. We have some rectangles. We have some triangles. And we have now partitioned it into 3 based on their labels. 3 labels. Now, if this is the data set, let's try to build a decision tree that explains the data set and the partition. Or in other words, a tree that explains the partitioning of the data set. Because when we say again a data set consists of not just the input but also the labels. And we are building a supervised classifier or a decision tree here, which is a supervised classifier. So naturally, we have to learn the partitioning or the basically learn a classifier that explains this partitioning. or at least that can perform this partitioning for a new unseen scenario. So, for example, let me ask you a simple question here, a seemingly simple question or an easy question based on the data set. So, if we had to guess, what would be the label for a red triangle? I'm not sure if there are takers for A, B, and C, all of those, but if you ask me, I believe it will be label B. And now, what is my justification for that? I would say everything that is red has so far been assigned to B. Everything that has been a triangle also has been assigned to B. So please note that red triangle is not present in the input. It's an unseen instance. But I could say that all the red shapes are assigned to label B and all the triangles are also assigned to label B. Actually, I don't need both. I probably at this point, I would say everything that is red, because there is red circle, red rectangle, both of them go to B. Everything that is red has been assigned to label B. So I would give that. As an alternative argument, which is independent. So please understand that the first argument was everything that is red is in label B. That suffices to say that at this moment, it belongs to label B. I can make an additional argument, not additional, I can make an alternative argument, completely independent of the other, that every triangle is in label B. So I would rather give a red triangle also in label B, because that's also a triangle. Now, this was a hand-picked, or this was a nitpicked convenient example. We have chosen to drive home the point. Now let's try to see from a learning perspective how exactly we can generalize this inference or the deduction that I made. So just like any other machine learning problem, the first question is that what can be our feature space? So I would say the color and shape can form a good feature space. It's pretty simple, right? I have two features, color and shape. Now, based on the data set here, we have three values for colors. We have a blue, we have a red, and we have a green. As we have previously seen, it is quite straightforward when the color is red. Based on the data set, the color red is present only in label B. I can assign label B right away. So I will say label B. So what I will do is that I will use this color, this pinkish color, pinkish red, to represent terminal nodes, and for the non-terminal nodes, I will represent using a different color, maybe orange. So now, if you see the color blue, it leads to multiple possibilities. We can find blue in both label C and label A. So we need to gather more information before arriving at a decision. So if the color was red, it was pretty straightforward, as we have seen previously. We assign it to label B, that's a decision, we don't have to think any further. But unfortunately, for color blue, I will come to green later, but for the time being, for color blue, it is present in both label A and C. So just based on the color, I can't come to a conclusion what is the class or what is the label. So So at this point, what I will do is that I will create a subtree. Assume it's a circular node. And now here there is no confusion. I can simply use the second feature, which is shape. I will use the shape feature. And now based on the shape, I have to make subsequent decision. So if we are at this point, then we already are considering only those instances which are of color blue. We are ignoring everything else. So in label A, if you look at label A, or maybe let's go top down itself. So if you look at the shapes now, for all those shapes which are of color blue, whenever there is circle, it has been assigned to label C. So I will say circle. It can be a circle or ellipse, it doesn't matter. And whenever it is a rectangle, it has been assigned a label A. So I will say circle means C, rectangle means A. So what happened here? We started off with the root node, which happens to be the color node. We are considering only those subset of data points where the color is blue. Amongst them, if the shape is a circle, we seek that it is in C. If the shape is a rectangle, it is in A. If the shape is a triangle, it is B. Yeah. We are only considering those of shape blue because we have already taken this edge. Or in other words, in a more general sense, we have taken the path. If you have three features and if we needed all the three features to make a decision, and if we were at this point, I would have said that we have taken the path where the color is blue and the shape is circle, and whatever the third feature amongst that basically can tell us the class. Now let's do the same for label, now let's do the same for the color green. In color green also, again, we only have one feature, which is the shape feature, right? So in the green, I happen to have only either a circle or a rectangle. Yeah, it's either a circle or a rectangle. So if it's a rectangle, we go to label B, and if it's a circle, we go to label A. We do not have a means to tell for triangle, so we will stop here. So I believe we have arrived at the same tree as drawn previously. So we finally end up with a decision tree that represents the data set. Now to make predictions, I can simply use the tree and traverse the tree based on the feature values for the new previously unseen input. Let's take the example of a red triangle again. So please note that red triangle is not part of the data set. See, there is no red triangle. So it was not part of the construction of the tree. It's an unseen example as far as this tree or the learner is concerned. And what happens if you have a red triangle? It's a red triangle. So what happens if you have a red triangle? We will consider first the color, and if the color is red, we assign it the label B. So it belongs to label B. It's as simple as that. So you can see that even though it is a data structure which has stored the information hierarchically, it covers examples that is not even present in the data. In other words, this data structure generalizes to previously. This is more like a qualifier, so it need not be a big deal. The key term is generalizer. Previously unseen instances. I think I shouldn't do that. Yeah. So this is how decision trees are built. Now, that was purely for illustration purpose. For example, let's say, but you know, the learning is not that straightforward, because let's say, what happens if we have a green triangle, right? There is a green triangle now. Yeah. So we definitely can traverse one edge of the tree based on the color. So let's say we start off with the color, which is green. We reach to the next node and we see that we can't get a answer, just like in case of red. We don't get a final answer, we don't get a label. We need more information, and that is coming from the shape. But in the case of shape, it is a triangle, and for the path that starts with the color green, unfortunately, we don't have an edge that talks about the triangle. So basically we end up in a dead end, or rather on a non-terminal node or a non-leaf node with nowhere to go based on the feature value. Now that is possible, it need not always generalize, right? So how do we address such issues, right? Well, it seems we'll have to wait till the next lecture before we arrive here. But just keep this in mind on how these kind of issues can be handled. So before we conclude this lecture, I will probably get on to one more topic, just one additional topic. And let's see what exactly is the expressivity of decision trees. So, in other words, what Boolean functions can decision trees represent? The answer to that is that it is any Boolean function. So, every path from the tree to a root is a rule. As we mentioned, right? This is just if you look at the path, this path, it is nothing but color. It's a conjunction of two conditions, right? It's a color equal to blue and shape equal to triangle. Then it implies that label equal to B. I'm talking about this one, this edge, this path. So the full tree is equivalent to the conjunction of all the roots. So summarily, any Boolean function can be represented as a decision tree. So I will stop here. Thanks everyone for attending the lecture. We will now see how exactly we do learning, or how exactly a decision tree learner works. Thanks.